The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So we are going to switch directions. Rather than thinking about binary variables, these Ising variables that were discrete, think again about our lattice. But now at each site, we put a spin that has unit magnitude but m components. That is, Si has components 1, 2 to n, and the constraint that the sum over alpha Si alpha squared is unity. So clearly, if let's put it here explicitly, alpha 1 to n, so that when I look at the case of n equals to 1, essentially I have one component whose square has to be 1, so it's either plus or minus. We recover the Ising variable. For n equals to 2, it's essentially a unit vector whose angle theta, for example, can change in 3 dimensions. It would be exploring the surface of a cube. And we also assume that we have a weight that tends to make spins to be parallel. So we will use essentially the same form as the Ising model. We sum over near neighbors. And the interaction, rather than sigma I, sigma j, we put it as Si dot Sj, where these are the dot product of two vectors. Let's call, say, the dimensionless interaction in front K0. So when we want to calculate the partition function, we need to integrate over all configurations of these spins. Of this weight. Now for each case, we have to do n components, but there is a constraint, which is this one. Now, I'm going to be focused on the ground state. So when t equals to 0, we expect that spontaneously a particular configuration will be chosen. Everybody would be aligned to that configuration. Without loss of generality, let's choose aligned state to point along the last component. That is, all of the Si at t equals to 0 would be of the form 0, 0, except that the last component is pointing along some particular direction. Okay? So if it was, let's say, 2 components, let's say the y component would always be 1. They will be aligned along the y direction. Now, yes? Question?
Yeah.
Yes?
What dimensionality is the lattice?
Can be anything. So basically, we have 2 parameters as usual. N is the dimensionality of spin, and D could be the dimensionality of our lattice. In practice, for what the calculations that we are going to be doing, we will be focused in D that is close to 2. Okay? Okay. Now, if we add fluctuations at finite t, what happens is that the state of the vector is going to change. So this Si at finite temperature would no longer be pointing along the last component. It will start to have fluctuations. Those fluctuations will change the 0 from the ground state to some value. I'll call it pi 1, the next one pi 2, all the way to pi n minus 1. And since the entire thing is a unit vector, the last component has to shrink to adjust for that, so we will indicate the last component by sigma. So essentially, the subspace of fluctuations around the ground state is captured through this vector pi that is n minus 1 dimensional. And this corresponds to the transverse modes that we were looking at when we were doing the expansion of the Landau-Ginzburg model around its symmetry broken state. In this case, the longitudinal mode essentially is infinitely stiff. You don't have the ability to stretch along the longitudinal mode because of the constraint that we have put over here. So if you think back, we had this wine bottle or Mexican hat potential, and the Goldstone modes corresponded to going along the bottom, and how easy it was to climb this Mexican hat was determined by the longitudinal mode. In this case, the Mexican hat has become very, very stiff to climb on the sides, so you don't have the longitudinal mode, you just have these Goldstone modes. Now, the cost to pay for that is that I have to be very careful in calculating the partition function. If I'm integrating over the n components of some particular spin, I have to make sure that I remember that the sum of all of these components is 1. So I have to integrate subject to that constraint. And the way that I have broken things down now, I'm integrating over the n minus 1 components of this vector pi. And this additional direction, d sigma, but I can't do both of them independently because there's a delta function that enforces that sigma squared plus pi squared equals to 1, where pi squared corresponds to the magnitude of this n minus 1 component vector. And essentially, I can solve for this delta function and really replace this sigma over here with square root of 1 minus pi squared. But I have to be a little bit careful in my integrations, because this delta function I can write as a delta function of sigma plus or minus square root of 1 minus pi squared. And there is a rule that if I use this delta function to set sigma to be equal to square root of 1 minus pi squared, like I have done over here, I have to be careful that the delta function of a times x is actually delta function of x divided by modulus of a. So essentially, I have to substitute something here. So this is, in fact, equal to the integration in the pi directions. Because of use of this delta function to set the value of sigma, I have to divide by the square root of 1 minus pi squared. Okay? Which actually shortly we will write this in the following way. I guess there's an overall factor of 1/2, but it doesn't really matter. So, yes?
So what do you do with the fact that there are 2 places where the delta function is on?
Okay, I'm continuously connecting to the solution that starts at 0 temperature with a particular state. So I have removed that ambiguity by the starting point of my theorem. Okay. But if I was integrating over all possibilities, then I should really add that one too, and really it just makes the partition function be the sum of two equivalent terms, one around this ground state, one another around the other ground state.
The product is supposed to be for lattice sites, right? For the integration variable, not for the
right.
spatial dimensionality.
Oh, okay, so I did something bad here. Right, so here I should have written. So this is an n-component integration that I have to do on each site. Now let's pick one of the sites. So let's say we pick site number I. For that, I have a small n integration to do. Okay. What does it say? It basically says that if, for example, I am looking at the case of n equals to 2, then I have started with a state that points along this direction, but now I'm allowing fluctuations pi in this direction. Okay? That I can't simply say that the amount of these fluctuations pi is going, let's say, from minus infinity to infinity, because how much pi I have changes actually whether it is small or whether it is large, where I'm down here. And so there is constraints, let's say, on how big pi can be. Pi cannot be larger than 1. And essentially a particular magnitude of pi, how much weight does it have? It is captured by this. So that's one thing to remember when we are dealing with integrations over unit spins and we want to look at the fluctuations. The other choice of notation that I would like to do is the following, that I said that my starting Hamiltonian is K0 sum over all nearest neighbors Si dot Sj. Okay. Now in the state where all of the spins are pointing in one direction, this factor is unity. So the zero temperature states gets a factor of 1 per each bond. Let's say we are on a hypercubic lattice. There are d bonds per site. So at 0 temperature, I would have ndk0, basically the value of this ground state. And then if I have fluctuations from that state, I can capture that as follows, as minus k0 over 2. It's a reduction in this energy, as sum over ij si minus sj squared over 2. I put the 2 already down here. And you can check that if I square these terms, I will get 1, 1, 1/2. It basically reproduces this. It actually goes over here. And the dot product minus 2si dot sj cancels this minus 1/2, basically gives you exactly this. Okay? So the reason I write it in this fashion is because very shortly I want to switch from going and doing things on a lattice to going to a continuum, and you can see that in this form, summing over the difference between near neighbors, I very nicely can go to a gradient squared. Okay. So essentially that's what I want to do. Whenever I have a sum over site, I want to replace it with an integral over space. And I guess to keep things dimensionless, I have to divide by a to the d. So I can call that a density that I have to include, which is also the same thing as the number of lattice points per the volume of the box. So my minus beta h in the continuum goes over to whatever the contribution of the completely aligned state is, and then whatever the difference of the spins is, because of these small fluctuations, I will capture through an integration of gradient of s squared. Okay? And I call the original coupling, that was basically the strength of the interaction divided by kt k0. Clearly, in order to get the coupling that I have in the continuum, I have to have this factor of a to the d, but then in the gradient, I also have to divide by distance. So there is some trivial factor of a to the 2 minus d that relates these two factors from the other way around. Doesn't matter.
Question.
Yes.
Have we, this step is only valid for cubical?
Yes.
Yeah.
Yeah, so if it was something like a triangular lattice or something, there would be some numerical factor here.
Oh, but I mean the path, like writing the difference in the spin squared as the gradient squared? Like if it were a triangular lattice?
Yeah. So the statement is that whatever lattice you have, what am I doing at the level of the lattice? I'm trying to keep things that are close to each other aligned. So when I go to the continuum, how is this captured? It's a term like a gradient squared. Now, on the hypercubic lattices, the relationship between what you put on the bonds of the hypercubic lattice and what will go in the continuum is immediately apparent. If you try to do it on the triangular lattice, you still can, and you'll find that at the end of the day, you will get a factor of square root of 3 or something like that. So there's some numerical factor that comes into play. Okay? And then at the end of the day, I also want to replace this gradient of s squared naturally in terms of essentially S has n components, n minus 1 of them are pi, and 1 of them is sigma. So this would be minus k over 2 integral d dx. I have gradient of the pi component and the gradient of the sigma component squared. So after integrating sigma using the delta functions, and going to the continuum limit, the partition function that we have to evaluate up to various non-singular factors, such as this constant over here, is obtained by integrating over all configurations of our pi field, now regarded as a continuously varying object on the d-dimensional lattice. And the weight, which is as follows. There is a gradient of pi squared, essentially this term over here. There is the gradient of the other term. The other term, however, if I use the delta function, is square root of 1 minus pi squared. And then there's this factor from the integration that I have to be careful. which I can also take to the exponent and write as, again, this density times log of 1 minus pi squared. There's, I think, a factor of 1. Okay. So the weight that I had started with S dot S was kind of very simple looking, but because of the constraint was hiding a number of conditions. And if we explicitly look at those conditions and ask what is the weight of the fluctuations that I have to put in the around the ground state, these Goldstone modes, that is captured through this Hamiltonian. Part of it is this old contribution from Goldstone modes, the transverse modes that we had seen. But now being more careful, we see that these Goldstone modes, I have to be careful about integrating over them because of these additional terms that capture essentially the original full symmetry, full rotational symmetry that was present in integration over S. Yes?
The integration, the functional integration, isn't phi should be limited to a sphere of 1?
This will kill you. So I put that constraint over here. And it's not just that it is limited to something, but for a particular value of pi, it gets this additional weight.
But isn't that only valid when pi squared is smaller than?
Yeah, so if you like, once I try to take my integrals outside that region, that factor says the weight is 0. Okay. All right, so this entity is called the nonlinear sigma model. And I never understood why they don't call it the nonlinear pi model, because we integrate immediately the sigma. That's how it is. Okay. So what we are going to do, if we had essentially stopped at the first term, not included any of the other things, we would have had the analysis of Goldstone modes that we had done previously. The effect of these things, you can see if I start making expansion in powers of pi, is to generate interactions. There will be nonlinear terms among the pi's. So these Goldstone modes that we were previously dealing with as independent modes of the system are actually nonlinearly coupled, and we want to know what the effect of that is on the behavior of the entire system. Okay? So whenever faced with a nonlinear theory, we have to do some kind of a perturbative analysis. And the first thing that you may be tempted to do is to expand in powers of pi and then look at the Gaussian part and then higher order parts, etc. That's a way of doing it, but there's actually another way that is more consistent, which is to organize the terms in this weight according to powers of temperature. Because after all, I started with a 0 temperature configuration, and I'm hoping that I'm expanding for small fluctuations. So my idea is to, I know the ground state, I want to see what happens if I go slightly beyond that, and the reason for fluctuations is temperature. So organize terms in this effective Hamiltonian for the pi's in powers of temperature. temperature. By this I mean the inverse of this coupling constant K, because clearly again, if I go through my whole derivation, you can see that I wrote minus beta H, so K0 should be inversely proportional to temperature. K is proportional to K0 should be inversely proportional to temperature. So up to some overall coefficient, let's just define temperature to be something like this. Now, we see that at the level that we were looking at things before, from this term, it's kind of like a Gaussian form, where I have something like K, which is the inverse temperature pi squared. So just on dimensional grounds, up to functional forms, etc., we expect pi squared to be proportional to temperature at the zeroth order, if you like. Because again, if temperature goes to 0, there is going to be no fluctuations. As I go away from 0 temperature, the average fluctuations will be 0. Average squared will be proportional to temperature. It all makes sense. So then if I look at this term, I see that dimensionally it is inverse temperature. Pi squared is of the order of temperature. So this is dimensionally t to the 0. Whereas if I start to expand this log, I can start to expand as minus pi squared plus pi squared, pi to the 4th over 2, pi to the 6th over 3, and so forth. You can see that subsequent terms in this series are higher and higher orders in this temperature. This will be order of temperature, temperature squared, temperature cubed. And already you can see that this term is small compared to this term. So although this is Gaussian term, and I would have maybe been tempted to put it in the 0th order Hamiltonian, if I'm organizing things according to powers of temperature, my 0th order will remain this. This will be contribution to 1st order, 2nd order, 3rd order. And similarly, I can start expanding this. Square root is 1 minus pi squared over 2. So then I take the gradient of minus pi squared over 2. I will get pi gradient of pi. You can see that the lowest order term in this expansion will be pi gradient of pi squared, and then higher order terms. And this is something that is order of pi to the 4th. So it is order of temperature squared multiplied by inverse temperature. So this is a term that is contributing to order of t to 0, to t to the 1. So basically, at order of t to 0, I have as my beta h0 just the integral ddx k over 2 gradient of pi squared. While at order of t to the 1st power, I will have a correction which has 2 types of terms. One term is this k over 2 integral ddx pi gradient of pi squared, coming from what was the gradient of sigma squared. And then from here, I will get a minus rho over 2 integral ddx pi squared. And then there will be other terms at order of t squared, u2, and so forth. Okay? So I just reorganize terms in this interacting Hamiltonian in what I expect to be powers of this temperature. Now, clearly, one of the first things that we will do is to look at this and realize that it can be decomposed into modes by going to Fourier space. So I do a Fourier transform, and this thing becomes k over 2 integral ddq divided by 2 pi to the d, q squared pi tilde of q squared. So let's write it as pi tilde of alpha pi tilde of minus q. And again, as usual, we will end up needing to calculate averages with this Gaussian rate. And what we have here is that P alpha of Q1, P beta of Q2 with this zeroth order weight. The components have to be the same. The sum of the two momenta has to be 0. And if so, I just get K Q squared. Okay. Now I can similarly Fourier transform the terms that I have over here. So the interaction Q1. First one becomes rather complicated. We saw that when we have something that is 4 powers of a field, and when we go to Fourier space, rather than having one integral over x, we ended up with multiple integrals. So I will have essentially Fourier transform of 4 factors of pi. For each one of them, I will have an integration. So I will have ddq1, ddq2, ddq3. And the reason I don't have the 4th one is because of the integration over x, forcing the 4 q's to be add up to 0. So I will have pi alpha q1, pi alpha of q2. Okay. Now note that this pi gradient of pi came from a gradient of pi squared, which means that the 2 pi's that go with this carry the same index. Whereas for the next factor, pi gradient of pi, they came from a different one. So I have pi q3, pi beta minus q1 minus q2 minus q3. Okay. Now, if I had just written this, this would have been the Fourier transform of my usual 4th order interaction, but that's not what I have because I have 2 additional gradients. And so 2 of these factors, actually, I had to take the gradient first. And every time I take the gradient in Fourier space, I will bring a factor of iq. So I will have here iq1 dotted with iq, let's say 3. Okay. So the Fourier transform of the leading quartic interaction that I have is actually the form that I have over here. There is a trivial term that comes from Fourier transforming this pi squared, because when I Fourier transform that, I get simply pi alpha of q squared. Yes?
Does it matter which q's you're pulling out as the gradient?
You can see that these 4 pi's over here in Fourier space appear completely interchangeably. So it really doesn't matter, no. Because by permutation and reordering these integrations, you can move it into something else. No, there is, I shouldn't. I'll draw a diagram that corresponds to that that will make one constraint apparent. So when I was drawing interaction terms for m to the 4th theory for Landau-Ginzburg, and I had something that had 4 interactions, I would draw something that has 2 lines, but the 2 lines had 2 branches. And the branching was supposed to indicate that 2 of them were carrying 1 index and 2 of them were carrying the same index. Now, I have to make sure that I indicate that the branches of these things additionally have these gradients or the IQs associated with them. And I make a convention, the branch or the Q that has the gradient on it, I will put a line. Now you can see that if I go back and look at the origin of this, that one of the gradients acts on one pair of pies and the other acts on the other pairs of pies. So the other dashed line I cannot put on the same branch, but I have to put over here. So the one constraint that I have to be careful is that these IQs should pick one from alpha and one from beta. Okay. So this is the diagrammatic representation. Okay. So what I can do is to now start doing perturbation in these interaction U1, let's say to the lowest order, to see what the first correction because of fluctuations and interactions of these Goldstone modes are. But rather than do things in 2 steps, first doing perturbation, encountering difficulty, and then converting things to renormalization group, which we've already seen that path and that story in dealing with Landau-Ginzburg model, let's immediately do the perturbative renormalization group of this model. Okay. So what I am supposed to do is to note that all of these theories came from some underlying lattice model. I was careful in drawing for you the first lattice model originally, which means that there is some cutoff here, some lattice cutoff, which means that when I go to Fourier space, there is always some kind of a range of wave numbers or wave vectors that I have to integrate with. So essentially, my pi's are limited after I do a little bit of averaging, if you like, that there is some shortest wavelength and the corresponding largest wave number lambda implicit in it. And the procedure for RG, the first one, was to think about all of these pi modes and break them into 2 pieces, the ones that corresponded to the short wavelength fluctuations that we want to get rid of, and the ones that correspond to long wavelength fluctuations that we would like to keep. Okay? So my task is as follows, that I have to really calculate a partition function over here, which in its Fourier representation indicates averaging over all modes that are within this orange, but those modes I'm going to represent as the pi lesser as well as the pi greater. Each one of these pi's is, of course, an n-1 component vector. And I have a weight that is obtained by substituting pi lesser or pi graters in the expressions that I have up there. And we can see already that the 0th order term, as usual, nicely separates out into a contribution that we have for pi lesser, a contribution that we have for pi greater, and that the interaction terms will then involve both of these modes, and in principle I could proceed and include higher and higher order. Now, I want to get rid of all of the modes that are here so that I have an effective theory governing the modes that are the longer wavelengths once I have gotten rid of the short wavelength fluctuations. So formally, once I have integrated over pi greater in this double integral, I will be left with the integration over the pi lesser field. And the exponential gets modified as follows. First of all, if I were to ignore the interactions at the lowest order, the effect of doing the integration of the Gaussian modes that are out here will, as usual, be a contribution to the free energy of the system coming from the modes that I integrated out. And clearly, it also depends, I forgot to say, that the range of integration is now between lambda over b to lambda, where b is my renormalization factor. Okay? Yes?
Because you're coming from a lattice, does the particular shape of the Brillouin zone matter more now, or still not really?
It is in no way different from what we were doing before in the Landau-Ginzburg model. In the Landau-Ginzburg model, I could have also started by putting spins or whatever degrees of freedom on a lattice. And let's say if I was a hypercubic lattice, I would have had a Brillouin zone such as this. And the first thing that we always said was that integrating all of these things gives you an additional, totally harmless component to the free energy that has no singular part in it. So we are always searching for the singularities that arise at the core of this integration. Whatever you do with the boundaries, no matter how complicated shapes they have, they don't matter. Okay? So going back here, if we had ignored the interactions, integrating over pi greater would have been giving me this contribution to the free energy. And of course, beta h0 of pi lesser would have remained. But now the effect of having the interactions, as usual, it is like integrating e to the minus u with the weight over here. So I would have an average such as this. And we do the cumulant expansion as usual. And the first term that I would get is the average of this quantity with respect to the Gaussian weight, integrating out the high component modes, higher frequency modes, and higher order collections. Okay? Yes?
So right here you're doing two expansions kind of simultaneously. One is you had nonlinear model that you expand to different powers of temperature, and then you further on expand it in cumulants to be able to account for it.
No, because I can organize this expansion in cumulants in powers of temperature. So this U has an expansion that is U1 plus U2, etc., organized in powers of temperature.
Okay.
And then when I take the first cumulant, you can see that the average, the lowest order term would be
the first cumulant is linear in temperature, and that's what you want?
Right. So I'm being consistent also with the perturbation that I had originally stated. Actually, since I drew a diagram for the first term, I should state that this term, since we are now also thinking of it as a correction in U1, I have to regard it as 2 factors of pi, so I could potentially represent it by a diagram such as this. So diagrammatically, my U1 that I have to take the average is composed of these 2 entities. Okay. So what I need to do is to take the average of that expression. Right? So I can either do that average over here, take the average of this expression, or do it diagrammatically, and let us go by the diagrammatic route. Okay? So essentially what I'm doing is that every line that I see over there that corresponds to a pi, I'm really decomposing into 2 parts. One of them I will draw as a straight line that corresponds to the pi lesser that I'm keeping, or I replace it with a wavy line, which is the pi greater that I would be averaging over. Okay? So the first diagram, I had essentially something like this. Actually, the second diagram, the one that comes from rho pi squared, it's actually trivial, so let's go through the possibilities. I can either have both of these to be pi lessers, sorry, pi graters. So this is pi greater, and when I have to do an average, then I can use the formula that I have in red about the average of 2 pi graters. And that would essentially amount to closing this thing down. And numerically, it would give me a factor of minus rho over 2 integral ddk over 2 pi to the d in the interval between lambda over b lambda. And I have the average of pi alpha gives me a factor of delta alpha alpha. Summing over alpha will give me a factor of n minus 1. And the average would be something like k squared. So I would have to evaluate something like this. But at the end of the day, I don't care about it. Why don't I care about it? Because clearly, the result of doing this is another constant. It doesn't depend on pi lesser. So this is an addition to the free energy once I integrate modes between lambda over b to lambda. There is a contribution to the free energy that comes from this term. It doesn't change the weight that I have to assign to configurations of the pi lesser field. That's another possibility. Another possibility is I have one of them being a pi greater, one of them being a pi lesser. Clearly, when I try to get an average of this form, I have an average of 1 factor of pi with a Gaussian field that is even. So this is 0. Don't have to worry about it. And finally, I will get a term which is like this, which doesn't involve any integrations. And it really amounts to taking that term that I have over there and just making both of those pi's to be pi lessers. So it's essentially the same form that will reappear, now the integration being from 0 to lambda over. So we know exactly what happens with the term on the right. Nothing useful or important information emerges from it. If I go and look at this one, however, depending on where I choose to put the solid lines or the wavy lines, I will have a number of possibilities. One thing that is clearly going to be there is essentially I put pi lesser for each one of the branches. Essentially, then it will like this one. It is reproducing the integration that I have over there, except that, again, it only goes between 0 and lambda over p. Okay? And now I can start adding wavy lines. Any diagram that has one wavy line, and I can put the wavy line either on that type of branch, or I can put it on this type of branch. It has only one factor of pi. By symmetry, it will go to 0 like this. There will be things that will have 3 factors of pi lesser. And all of these, again, because I'm dealing with an odd number of factors of pi greater that I'm averaging, will give me 0. There is one other thing that is kind of interesting. I can have all 4 of these lines wavy. And if I calculate that average, there's a number of ways of contracting these 4 pi's that will give me non-trivial factors. But these are also contributions to the free energy. They don't depend on the pi's that I'm leaving out. So I don't have to worry about any of these diagrams so far. Okay. Now, I dealt with 0, 1, 3, and 4 wavy lines. So I'm left with 2 wavy lines and 2 straight lines. So let's go through those. I could have one branch be wavy lines and one branch be straight lines. Okay. And then I take the average of this object. I have a pi greater here, and therefore I can do an average of 2 of those pi greaters. That average will give me a factor of 1 over k squared. I have to integrate over that. But one of these branches had this additional dash thing that corresponds to having a factor of k. So the integral that I have to do involves something like this. And when I integrate over the entirety of the k integration, this is an odd power, and so that will give me 0 also. So this is also 0. And there's another one that is like this, where I go like this. Sorry. Yeah. And although I do the same thing now with 2 different branches, the k integration is the same, and that vanishes too. So you say, is there anything that is left? The answer is yes. So the things that are left are the following. I can do something like this. Or I can do something like this. So these are the 2 things that survive and will be non-trivial. You can see that this one will be proportional to pi lesser squared, while this one is going to be proportional to gradient of pi lesser squared. So this one will renormalize, if you like, this coefficient, whereas this one will modify and renormalize our coupling strength. So it turns out that that is really the more important one. But let's calculate the other one too. So let's, yes?
Why did we connect the ones down here into loops but left all the ends free in the other ones? Is that just a matter of cases how to write the diagram, or does that signify something?
Could you repeat that? I'm not sure I understood.
So when we had two wavy lines both coming out on one of the diagrams and this line, they just stopped. We connected them together when we were writing the ones in the bottom line.
Okay, so basically I start with an entity that has two solid lines, let's say, and two wavy lines, right? Mm-hmm. Okay, and what I'm supposed to do is to do an integration, an average of this over these pi graters. Okay, now the process of averaging essentially joins the two branches. If I had a momentum here Q1 and a momentum here Q2, if I had an index here alpha and an index here beta, that process of averaging is equivalent to saying the same momentum has to go through, the same index has to go through. There is no averaging that is being done on the solid lines, so there is meaningless to do anything. Okay. Okay. So this entity, okay, is the following. I have k over 2. Let's call it legs 1, 2, 3, 4. Integral Q1 and Q2, but Q1 and Q2 you can see explicitly are solid. So these are the integrations from 0 to lambda over b. I have an integration over Q3, which is over a wavy line. So it's between lambda over b and lambda. If I call this branch alpha and this branch beta, from here I have actually pi lesser alpha of Q1, pi lesser beta of Q2. I should have put them outside the integration, but doesn't matter. And then here I had pi alpha of Q3, pi beta of Q4, but these also had these lines associated with them. So I have here actually an I Q3 and I Q4. Again, Q4 has to stand for minus Q1, minus Q2, minus Q3 from this. And then I had the pi here, which gives me, because of the averaging, a delta alpha beta. And then I will have an integration that forces Q3 plus Q4 to be 0. And then I have k Q3 squared. Okay. Now Q3 plus Q4 is the same thing as minus Q1 minus Q2, if you like, because of that constraint. So I can take that outside the integration. There's no problem with that. I have one integration left, which is 1 over kq3 squared, but these two then become the same. These pi's I will take outside. I note that because of this constraint q1 and q2 being the same, these two really become one integration that goes between 0 and lambda over b. And these two indices have been made to be the same. So I have pi alpha of q, this q squared. All right. Then I have the integration from lambda over b to lambda, vd q3, 2 pi to the d. Here I had iq3, iq4, but q4 was said to be minus q3. So the two i's and the minus cancel each other, and I will get a factor of q3 squared. And then here I have a factor of k q3 squared. Okay? So the overall thing is just, we can see that the k's cancel. I have one factor, integral vd q 2 pi to the d. I have pi alpha of q squared, and these are q lessers. I integrated out this quantity. The q3's vanish. So I really have the integral of q3 over 2 pi to the d. Now, if I had done the integral of q3 2 pi to the d all the way from 0 to lambda, what would I have done? If I multiply with the volume here, that would have been the number of modes. So this is, in fact, n over v, which is the quantity that I have called the density. But what I'm doing is, in fact, doing just a fraction of this integral from 0 to lambda over v. So if I do the fraction from 0 to lambda over v, then I will get 1 minus b to the minus d. From lambda over b to lambda. Then if I had done it all the way to from 0 to lambda, I would have had 1. But I'm subtracting this fraction of it. So the answer is rho 1 minus b to the minus d. So the overall thing here gets multiplied by rho 1 minus b to the minus d. It just will correct that factor of density that we have. We'll see shortly. It's not something to worry about. The next one is really the more interesting thing. So here, we have this diagram, which is k over 2, integral from 0 to lambda over b. Essentially, I will get the same structure. This time, let me write the pi alpha lesser of q1, pi beta lesser of q2 outside the last integration. I have the integral from lambda over b to lambda, vd of q3, 2 pi to the 3d. And I will have the same delta function structure, except that now these factors of iq become iq1 times iq2. So I can put them outside already. And then I have here the delta function. So the only difference is that previously the q squared was inside the integration. Now the q squared is outside the integration. So the final answer will be k over 2, integral 0 to lambda over d, dd q 2 pi to the d. I have a q squared, pi of q lesser squared. And the coefficient of that would look like what I had before, except without this factor. So it's the integral from lambda over b to lambda, dd of q3 divided by 2 pi to the d, 1 over k q3 squared. Okay. So once I do explicitly this calculation, the answer is going to be a weight that only depends on this pi lesser that I'm keeping, and I will indicate that by beta h tilde as usual. That depends on this pi lesser. And we now have all of the terms that contribute to this beta h tilde. So let's write them down. There's a number of terms that correspond to changes in the free energy. So we have a V delta FB at the 0th order, contribution to delta FB at the first order, that are essentially a bunch of diagrams, both from here as well as from here, but we don't really care about. Okay. Then we have types of terms that look like this. I can write them already after Fourier transformation in real space, so let me do that. I have integral ddx in real space, realizing that my cutoff has been changed to dA. Things that are proportional to gradient of pi lesser squared. Now, gradient of pi lesser squared is the thing that in Fourier space becomes q squared pi lesser squared. And what is the coefficient? I had k over 2, which comes from here. If I don't do anything, I just have the 0th order modes acting on these. But I just calculated a correction to that. That is something like this. Right? So in addition to what I had before, I have this correction, k over 2 times this integral, and I'm going to call the result of this integral to be I sub d okay. See that this integral is proportional to 1 over k. And then the integration, let's call the result of the integration I d of t, because it depends on both the dimension of integration as well as the factor b through here. So I have 1 over k I d of t. So that's one type of term that I have generated. I started from this 0th order form, and I saw that once I make the expansion of this to the lowest order, I will get a correction to that. And actually, just to sort of think about it in terms of formulae, you see what happened was that the first term that I had over here was pi gradient of pi repeated twice. And what I did was I essentially did an average of these two pi's and got a correction to gradient of pi squared, which is what was computed here and appears here. The next term that I have is this term by itself, now calculated with the pi lessers only, so this object. So I will write it as k over 2 pi gradient of pi squared. There is no correction. Final term that I have is this term. So I have minus rho over 2 pi lesser squared. And then the correction that I had was exactly the same form. It was 1 minus b to the minus t. The rho over 2 is going to be common to both of them. You can see that there is a rho and there's a 2. And so basically I have to add this to that. And to first order, this is the entirety of the things that I will get. Okay. So this, however, is just a coarse graining. It's the first step of the RG, and it has to be followed by the next two steps of the RG, where here you look at your field and you can see that the field is much coarser because the short distance cutoff, rather than being A, has been switched to BA. So you define your x prime to be x over b, so that you shrink, you get the same coarse pixel size that you had before. And you also have to do a change in pi, so you replace pi lesser with some factor zeta pi prime, so that the contrast will look fine. So once I do that, you can see that the effect of this transformation is that this coupling k will change to k prime. Because of the change of x with bx prime, from the integration I will get b to the d. From the two derivatives I will get b to the minus 2. From the fact that I replace 2 pi lessers with pi primes, I will get a factor of zeta squared. And then I will have this factor k 1 plus 1 over k id of b. So this is the recursion formula that we will be dealing with. Now there is some subtleties that go with this formula that are worth thinking about. Our original system had really one coupling parameter k, that because of the constraints of the full symmetry of this field S, part of it became the quadratic part that was the free field theory, but part of it made the interactions. But because of the spherical symmetry, the form of that interaction was fixed, and it had to be proportional to k. Now, if we do our renormalization group correctly, the full symmetry that we has to be maintained at all levels, which means that the functional form that I should end up with should have the same property, in that the higher order coefficient should be related to the lower order coefficient exactly the same way as we had over there. And at least at this stage, it looks like that did not happen. That is, we got a correction to this term, but we didn't get a correction to this term. We shouldn't be worried about that right here, because we calculated things consistently, corrections to order of t. And this was already a term that was order of t. So the real check is if you go and calculate the next order correction, you better get a correction to this term at next order that matches exactly this. And people have done that and have checked that, and that indeed is the case. So 1 is consistent with this. There are other kinds of consistency checks that happen all over the place, like the fact that this came back 1 minus 1 came out to be b to the minus t, so that the density is the same as before, consistent with the fact that you shrunk the lattice after all g so that the pixel size was the same as before, is a consequence of that. You may worry that that's not entirely the case, because when I do this, I will have also a factor of zeta squared. But it turns out that zeta is 1 plus order of temperature, as we will shortly see. So again, consistent, everything is consistent at this level that we've calculated things. And the only change is this factor. Now, the one thing that we haven't calculated is what this zeta is. Okay? So to calculate zeta, I note the following, that I start with a unit vector that is pointing at 0 temperature along this direction. Okay? Now, because of fluctuations, this is going to be kind of rotating around this. So there is this vector that is rotating. If you average it over some time, what you will see that the average in all of these directions is 0. The variance is not 0, but the average is 0. But because of those fluctuations, the effective length that you see in this direction has shrunk. Okay? How much has it shrunk by is related to this rescaling factor that I should choose. And so it's essentially average of something like 1 minus pi squared. But really, it is the pi lesser squares that I'm averaging over, which to lowest order is 1 minus 1/2 the average of pi lesser squared, which is 1 minus 1/2. Now, this is an n minus 1 component vector. So each one of the components will give you one contribution. The contribution that you get for one of these is simply the average of pi squared, which is 1 over k squared, which I have to integrate over k's that lie between lambda over b and lambda. Okay? And you can see that this is 1 minus 1/2 n minus 1. It is inversely proportional to k. And then the integration that I have to do is precisely the same integration as here. So it is again this id of e. Okay, so let me write the answer, say a couple of words about it, and then we'll deal with it next time. So k prime is going to be b to the d minus 2, the new interaction parameters. It is 1 factor of 1 plus 1 over k id of b. And then there is 1 factor of the square of zeta, so that gives you n minus 1 over k id of b times k. So we'll analyze this more next time around, but I thought I would give you the physical reason for how this interaction parameter changes. Let's say we are in 2 dimensions, so let's forget about this factor. In 2 dimensions, we can see that there is one factor that says at finite temperature, you're going to get weaker. The interaction is going to get weaker. And the reason for that is precisely what I was explaining over here. That is, you have some kind of a unit vector, but because of its fluctuations, you will see that it will look shorter, and it is less likely to be ordered. The more components it has to fluctuate, the shorter it will look like. So there is that term. So if this was the only effect, then K would become weaker and weaker, and you would have disorder. But this effect says that it actually gets stronger because of the interactions that you have among the modes. And to show you this to you, you can experiment for it yourself. So this is a sheet of paper. This bend is an example of a Goldstone mode because I could have rotated this sheet without any cost of energy. So this bend is a Goldstone mode that costs very little energy. Now this paper has the kinds of constraints that we have over here. And because of those constraints, if I make a mode in this direction, I'm not going to be able to bend it in the other direction. So clearly the mode that you have in this direction and this direction are coupled. That's kind of an example of something like this. Now, while it is easy to do this bend, because of this coupling, if thermal fluctuations have created modes that are shorter wavelength, and I have already created those modes over here, then you can experiment yourself. You'll see that this is harder to bend compared to this. You can see this already, okay? So that's the effect that you have over here. So it's the competition between these two, and depending on which one wins, and you can see that that depends on whether n is larger than 2 or less than 2. So essentially for n that is larger than 2, you'll find that this term wins, and you will get disorder in 2 dimension. N is less than 2, you will get order, like we know the Ising model can be ordered. So, but there's other things that can be captured by this expression that we will look at next time.